Okay, so welcome to this, which session is it? Day 2, session on planning and design. We're going to start off with Marja-Liisa Siikonen. She's unfortunately unable to join us in person today. Hopefully we'll get to speak to her after her talk, which is prepared on video. So Marja-Liisa Siikonen is well known to many of us, certainly in the traffic field. CEO of MLS Lift Consulting, had an MSc and PhD from Helsinki University of Technology in Finland. She's retired from Kony now, but still active, as you can see, after working for 34 years with control systems and transportation planning. She's published more than 100 articles and 250 patents in the field on people flow and elevator control systems, and she's author of her new book, People Flow in Buildings. And this actually was an invited paper, so we specifically invited Marja-Liisa to talk about her new book. And so here's Marja-Liisa.
Ladies and gentlemen, in this presentation, I make a short overview of the book People Flow in Buildings. First, I explain the motivation why this book was written. Then a short review of the highlights of the 5 parts in the book. At the end, some speculation of the future vertical solutions. In 1970s, 80s, Barney dos Santos published the book of Elevator Traffic Analysis, Design and Control. It is the fundamental work in elevator traffic and has inspired me in my research work throughout the years. Later, when planning customer projects, vertical transportation by Strakos has given a practical insight to the elevator planning. I have experienced the changeover from the relay controls to software-based systems from 1980s up to now. Also, elevator planning methods have developed during these years. This is all I wanted to write down to this new book. Then to the highlights of each part of the book. The first part handles with people flow measurement methods and measurement results. One of the findings of the research was that people flow move in batches in buildings. The observed mean batch size varies between 1 and 2, depending on the building type and the traffic pattern. According to the observations, passenger batches arrive randomly to the elevator lobbies, following compound Poisson process. In office uppeak, people usually arrive individually, where the batch size is 1, but during lunch hour, the batch size can be 1.5, according to the observations. In resort hotels, the batch size can be even 2. The second part of the book handles with solutions and vertical transportation technology of the current and future and past solutions. One of the suggested early multi-car solution was Odyssey, which was introduced by Otis in 1990s. Their elevator cabs move around the building using combination of elevator shafts and automated people mover. For short horizontal distances, the linear induction motor control moved the cabs smoothly on and off the elevator frame. what do you say, never became a product. Elevator performance can be calculated, and there are formulas for elevator round trips and other performance figures. But in addition to vertical traffic, also horizontal traffic has its own calculation formulas. This figure shows on the y-axis the people flow in persons per second per meter, how it increases when passenger speed increases, until it reaches a saturation point called full flow. There is a capacity density in persons per square meter, after which if the capacity or density increases, then there will be congestion, and finally the traffic is jammed if the density is high enough. This kind of phenomenon we can see in walkways, corridors, and staircases, for example. The calculation formulas can be verified with simulation. Part 4 concentrates on the simulation methods. One example in the book shows the simulated round trip time for the 3 traffic patterns: up peak, lunchtime, and down peak. The round trip time is the longest for the lunchtime traffic because there are stops in both directions. Round trip times are the shortest for the down peak. Similar effect can be seen for the number of stops per round trip. At certain point, the number of stops per round trip starts to saturate, and this depends on the cabin size of the elevators, and also of the number of served floors. Perhaps other things also. Another example made by simulation is the relative handling capacity for 3 different traffic mixes and different elevator systems and controls. For a single car elevator with conventional control, the up-peak handling capacity is scaled to 1. During lunchtime, the same elevator group can serve 30% more traffic, and in down peak even 50% more traffic. Here, a compromise boosting is the minimum of these boostings. For the conventional system, it is 1, no boosting. For the destination control, the boosting is 1.3, 30% more. And for the double deck system with conventional control, it is 60% more than with conventional system. The greatest increase in handling capacity comes with destination control double deck elevators. It increases the handling capacity to 2 compared to 1 with the conventional system. Simulation is also applied in part 5 that deals with the people flow planning. As an example, it shows the performance of the different elevator solutions in a super tall building. The elevator arrangements are selected by using the simulation method of ISO 8132. There is an uppeak traffic pattern and lunch-hour traffic pattern that we simulated. The building has 78 floors with 11,000 people, and 2 different elevator arrangements are applied here. One is that there are 7 groups, elevator groups, all starting from the ground. And there's a skylobby solution where 3 local groups start from the ground and 3 local groups from the skylobby. The shuttle elevator handles the traffic between the ground and the skylobby. Six different systems were analyzed, and especially the space demand in this building. The conventional control for the zone building, the first alternative, is scaled to 100. And the others are scaled to this conventional control. So destination control takes less, and double deck conventional control take less space than the original one. With double deck destination, only 60% of the of the space of the original one is required. The skylobby arrangement still decreases the space demand, and with a solution where double deck destination control serves the local groups, and in the shuttle group there is a multi-car system, such as multi, serving the traffic between ground and skylobby. It takes only about 1/3 of this original solution. Up to now, the limiting factor for tall buildings has been the weight of the ropes, which increases with the travel height. Also, the speed of the elevators has been a problem because it becomes harmful for the human ears when it exceeds 8 meters per second. Ropeless technology can avoid these problems, since in multi-car system with linear motor there are no ropes, and the elevators do not require high speeds. The handling capacity and waiting times can be adjusted by adding the number of cabins in the shaft. With the last analyzed arrangement where double decks with destination control served the local groups and a multi-system was used in the shuttle groups, someday Frank Lloyd Wright's dream of the mile-high building can be reached. This concludes my presentation. Thank you.